All right, so my plan was to go over, maybe I would just start and then whatever can be covered can be covered. And so one thing I want to talk about is one of the homework question, I think question 3, is doing a little bit more of the full conditional derivation, right? I don't know like how far along you have done it. And I do want to mention that even though right now we're relying on JAX for this model, you can derive all of the full conditionals here. It's not something like crazy. You can still do it. It's definitely a little bit more involved, but I do want to spend, let's just say like 10 minutes or 15 minutes before until we end for today, just to maybe just go over really quick of typically what people do when they try to derive full conditional. And now we have a much more complicated model because things are starting to be in a hierarchical way. So that's what I'm hoping to cover. So again, the model. So I will try to write as much as I know. And then if you have further questions, I mean, we can continue this on Thursday. I want to mention this today just because I know homework is due on Thursday. I was hoping to maybe help a little bit. So, so first of all, the data model that we have is Yij is normal of mu j and sigma. Okay, so we're working with the simpler case that you have a schedule-specific mean and then standard deviation shared across all of them. Okay, so. And then it's important to actually get the index right. So I is 1 from 1 to nj. Remember, nj is the number of, in this case, number of dramas in that schedule. And then j goes from 1 to capital J. That is total number of schedules that we have. Okay, so that's the data model. And the prior, I'm going to use the prior that we covered. So first of all, the first stage is mu j is IID, normal, mu and tau, right? And also good to keep the index right. J is 1 to capital J, okay? So first stage, and then second stage for this is we have mu is normal, what do we have? I think mu 0 and gamma 0. Here, there's no more index because we're working with one particular parameter. Okay. And of course, we also give tau a prior. In particular, it's gamma for 1 over tau squared. So that's we use, I think, alpha tau, and then beta tau here. Okay. And lastly, don't forget, we have this 1 over sigma, which is the not a two-stage prior, but sigma is being shared. And we use alpha sigma and then beta sigma to represent its mean and standard deviation. Okay. So typically, as you can see, that you're going to write out the data model and then list all of the priors together. And then, of course, the first step when you're trying to do the full conditional is to write the joint distribution of all of the unknown parameters in your model. Okay, so let's get it straight first. What are the parameters? We covered it just now when I was talking about the JAX code, but let's try to make sure that we get all of the parameters right. So Yij is data, okay, that's irrelevant. Mu j, right? And there are 4 of them, okay? Sigma is parameter, mu is hyperparameter, tau hyperparameter. That's it, okay? So this, they are hyper parameters, but in the end, we give them fixed numbers, so we don't make inference about them, so don't worry about them. Okay, so keep straight, like keep very clear about what is random. So first of all, what are the parameters? And second, how am I going to give priors for them? And then in the end, you can summarize everything together to come to your joint posterior. So now we identify all of the parameters. So we know that the joint posterior should be on what? All of the mu j's. So I'm going to write in this way, the mu j's, right? And sigma, mu, and tau. Okay. Everything else is supposed to be given. So you have what? All of the Yij and mu 0, gamma 0, alpha tau, beta tau, alpha sigma, beta sigma. Right? So what's being conditioned is given, or like say data is what you will be or like what will be given, and mu 0, all of those, they are fixed values in the way that we're fitting the model now. Okay. All right, so what this should be, we know that the joint posterior distribution should be the data, which is the likelihood, multiplied with all of the priors together. Okay, so I'm just going to write the first step for you. Might be a little bit complicated. So let's see. Let's write the prior first. So what do we have? We have mu j given mu and tau. Right. So this is the prior that we have for mu j. And what's important to notice here is that, well, you not only have one j, you have kept a number of j's together, and they're all independent. They're IID. So you should write a product sign outside. And I know it's a little bit confusing because we have pi and then the product, so they look very similar, at least the way that I write them. So make sure that you put the product, like say the index, on the thing that you're working with. Okay, so that's for mu j. What about for mu? You have pi mu given mu 0 and gamma 0. Okay. And for tau, you have 1 over tau squared over alpha tau, beta tau. And then lastly, you have the prior for 1 over sigma squared, which is depending on this two. Make sense? Yeah, Christian?
So since like conjugacy is not really a concern anymore, right?
It is. Okay, so I don't think we will be able to get that far today, but now I'm writing it generically right now, at least in the lower part, right? Like we're just collecting the terms that is necessary. But then later, if you try to derive the full conditionals, conjugacy plays an important role here.
So what is like, what's the, so the posterior is also normal?
Yeah, so in fact, okay, good question. So maybe that's all I can cover today. So in fact, the posterior, it's not a posterior, it's the full posterior, full conditional posterior distribution for each of the mu j is a normal.
Okay.
Yeah, and then the full conditional posterior distribution mu, it's a normal as well. And then for 1 over tau squared, it's a gamma. And for 1 over sigma squared, it's another gamma. Yeah, you're able to derive it. And I think I can carry on Thursday just because I think it's still important material to cover. I was hoping to do more so I can help a little bit more for the homework, which is related. I mean, not the same context, but it's the similar idea, okay? So conjugacy plays a role here later when you see that you're trying to find the terms, say for mu j, for mu, for 1 over tau squared, for 1 over sigma squared, okay? All right, and lastly, so in order to write the joint posterior, we have all of the priors now, right? And the last part is the likelihood. So the likelihood, all right, so let me write, so again, it's multiple products that you're gonna be doing if you're looking at this. So first of all, we know that each of the Yij follows a normal, right? So I can work with all of the Yij's in a given j. Okay, so what should I write? I should have Yij given mu j and sigma. It's going to be a normal density when you try to expand it, right? But let's get the dimension right first. So this is looking at all of the observations in, and I should write here, we have independence. And IID, let me do IID here. Yeah, because within the schedule, they're all follow the same normal. So if I'm only looking at all of the observations Yij in a fixed J, I will have the product, and they're IID. So I have the product of I from 1 to nj, because that's how many observations I have for that schedule, right? So this product is giving you all of the joint density of all of the Yij in the same J, right? Yeah. So that's only one J, and we have capital J number of them. So what you do is the whole thing, take the product of J from 1 to capital J. Okay. So this is new because in the past we're not doing anything hierarchical. Okay, everything is IID, and then the index only goes from like 1 to n, or the most complicated case we have seen is in the exam that I give you like the cutoff point and then try to move that around, but still you only have total number of n observations, and then nothing is being like nested in this way. Okay, but now it's more complicated. So you have in here the joint distribution of all of the observations in a particular schedule. And because everything is IID as well, so I also need to multiply all of the different possibility of J. So I do that outside. So yeah, on Thursday when we come back, I will develop this a little bit more. And as Cushing said earlier, the conjugacy only matters if we try to find the exact full conditional posterior distribution of all of the parameters. But JAX is very flexible. So I just want to mention that for the model that we just implemented in JAX, you can write it up yourself, okay? But if you start to play with the normal priors or whatever, because we saw some issues about those mu, you start to do new stuff, well, you can still try to derive, but probably you will never get there. And there are other methods that you can use if full conditional posterior distribution is not available. So next time I will mention them as well. And then we can see what we can do. So I know, I mean, homework is due on Thursday, so I wouldn't like ask you to try this out before Thursday, but I do want to build it up as if now. So here, yeah, so maybe just really quick and then we come back on Thursday. So this are all normal densities, right? Keep track of the mean and the standard deviation and make sure that you are doing the product, okay? So when you're doing product, because normal density has two parts, right? One of the square root of 2 pi, whatever sigma is, and then the other part is the exponent. So outside of the exponent is just going to the power, right? And then inside the exponent, the product outside of it becomes the sum. Okay, so we have seen this before, but you need to keep track and make sure. So this is only one normal density, nice and easy, I think. All of this are just gamma density, so nice and easy as well. This part, just work really carefully about it because it's two products together. I would do the inner one first and then the outer one. And when we come back on Thursday, but then each of this is a normal anyway. So it's only, yeah, it really matters later when you try to derive, say, oh, I want to get the full conditional posterior distribution for this mu j. What should I know? I need to get, say, we typically, when you have a lot of parameters, we just write this to indicate everything else, conditioning on everything else. Okay, I mean, you can keep writing if you want, but you can use it as a shorthand. So we know that in order to come up with this full conditional posterior distribution, in this whole thing, we have to collect the terms about mu j only. Okay, so really quick, where would mu j come from? Here, right? And some stuff in here. Yeah, but what are they? And how can I collect the terms and then recognize them ultimately to be a normal? I think that's still important to know, even though now we rely on JAX, you don't need to know the full conditional posterior. But overall, I think it's enhancing your understanding of those Bayesian methods. Okay, so on Thursday, we come back. and try to do that hopefully quickly and then move on. And Thursday, homework 4 is due. And there is one question about Gibbs sampler and deriving those. Not exactly the same context, but hopefully the setup that I did today can help you to get started if you are stuck about it. But stop by office hours today and tomorrow if you have questions. Okay. All right, thank you.